Yesterday, you guys learned about extrasolar planets. You got to watch a video and you got to read a little bit. And today, what we're going to do is this bottom line down here. Understand how we look for and study solar systems other than our own. We're going to move on and look at extrasolar planets. For short, we're going to call these exoplanets. Much easier to say. I want you guys to write these two questions down in your science journal, but leave a blank spot so that you can come back and answer them after you learn about them. And here is Neil talking about exoplanets.
Depending on who you talk to, our sun's got 8, maybe 9 planets circling around, including Earth. Until recently, we haven't been able to see any planets beyond our own solar system. None at all. The problem is, planets in deep space are rendered practically invisible by the blinding light of their suns. That's the challenge for the handful of scientists trying to track them down. The team of Paul Butler and Jeff Marcy started their quest in the 1980s. Marcy and Butler were confident that they had the best method for hunting down big planets and hoped they'd be the first to succeed, when a team of Swiss astronomers beat them to the punch. The first planet outside our solar system had been found. Most astronomers were skeptical. Although the planet was massive like Jupiter, the Swiss discoverers claimed it orbited its star, 51 Pegasi, in only 4 days. This seemed impossible. Earth takes 365 days to orbit the Sun, and Jupiter takes 12 years. Marcy and Butler felt certain there must be some mistake.
Almost every year for the last 100 years, somebody's claimed to have found the first extrasolar planet. And the one thing all those claims had in common was they were wrong.
And luckily, Paul Butler and I had telescope time the very next week. And we thought, well, we'll just go up and take data on this star, 51 Pegasi, and show that it probably doesn't really have a planet at all.
And when we got back and we analyzed all the data, we were stunned. We were stunned because their claim was right. There really was a Jupiter-like planet in a 4-day orbit. We were stunned because this was the first legitimate real planet ever discovered. And that furthermore, that these planets could be much stranger, much more bizarre than any theories that had ever been conjured before.
So what is an extrasolar? What is an extrasolar planet? An extrasolar planet or an exoplanet is any planet that is outside of our solar system. It's a planet that's going around a different star than the sun. When I started teaching this class 6 years ago, there was 1,932 of them. Then the next year there was 3,439, then 3,500, then 3,800. Last year there's 4,100. This year, I'm recording this in December, there's 4,300 of them. If I do this class again next year, I'm going to have to update this slideshow because we are continually finding new exoplanets every single year. In fact, there might be some that are announced today, whether it's the day that I'm recording or the day that you're watching. New exoplanets are being found all the time. So this is one of the PowerPoints that I have to update and change every single year that I teach this class. One of the things I don't have to update is when we found the first one. That was all the way back in 1995, before you guys were born. And that first ever planet that was ever found is known as 51 Pegasi b. It goes around the 51st brightest star in the constellation Pegasi, or Pegasus. Because of how we are finding exoplanets all the time and where we are looking, if you extrapolate that out to our entire galaxy, all throughout the Milky Way, there's estimated to be tens of trillions of planets. Not millions, not billions, trillions of planets in just our galaxy. And then you look out and there are billions and billions of galaxies out there. This is why I think there are aliens. There's just too many planets. There's too much stuff out there. Do I think the aliens have ever come here? No. The distances and times, it takes light millions and billions of years to travel across the universe. There's no way for aliens to do that. So do I think there's life out there? Almost certainly. Do I think it's been to Earth in a flying saucer? Probably not. This little icon basically tells you how many current exoplanets we have confirmed and what type they are. We're going to get into the different types of exoplanets a little bit later, but I mean, you can take a look for yourself. Now let's take a look at how we find them. We're going to talk about 5 different ways that we find exoplanets, 4 of them today and 1 of them tomorrow. So the first way that we find them is we take a photo of them. The problem is the same problem that we have when we try to look at the corona around the sun. The sun's so bright that it outshines the corona. Well, these distant stars are so bright that they outshine the planets that go around them. So what we need to do is actually cover up. When we cover up the brightness of a star, we can actually see the planet that's reflecting starlight in our telescopes. If we don't cover it up, the planet not giving off its own light is not anywhere near bright enough to see. One of the first images that we have of any planet, actual images on a camera of any planet, is Fomalhaut. Just kidding. Actually turns out that Fomalhaut is nothing more than an expanding dust cloud. As you can see, we continued to watch. It looked like a planet for the first couple years, but as we continued to watch, it just slowly disappeared. It most likely is a dust cloud from 2 icy objects, similar to comets, that smashed into each other out in what would be the Kuiper belt of this particular star. Not a planet, expanding dust cloud. I have my fingers crossed, and I'm hoping that as we get better and better technology, we're going to get better and better photos. We have a space telescope supposed to launch like 3 years ago, and then it got pushed back to 2 years ago, and then a year ago. It was supposed to launch this year, and now it's going to launch maybe next year, but probably it's going to get pushed back. It's called the James Webb Space Telescope, which is going to be about 10 times better than Hubble. It's going to be out past the moon. We're going to talk about this later this year, but hopefully we'll be able to maybe get better and better photos with better and better resolution, see things that are smaller and dimmer. Maybe, just maybe, we can actually see planets and maybe their atmosphere, or the continents if it's a water planet. Maybe we could see landmarks. And if we are super lucky, maybe we can see evidence of aliens. You never know. You never know. So what are the pros of this particular way of detecting planets? You're taking photos of exoplanets, which I think is freaking awesome. What's difficult about it, or what is a con? Well, it's very difficult to do. The conditions have to be absolutely perfect. Today, we can't get very good resolution because they are so far away. You have to cover up the distant star. Planets don't give off a lot of light. Write some of this stuff down. Because it's so difficult, of all the exoplanets that we found, only about 1% have been found using this method, actually taking photos of it. And last year, we had found 44 planets that we have pictures of. Today, we have 51 planets. So we have found 7 new planets this year. Next year, there will be more. I'm going to have to update this slide. It still stays at about 1%. Why can't we see all planets directly? Well, planets don't give off their own light, and that means that they're going to be lost in the glare of their host star. If they are in front of the star, obviously you can see the video, there's no chance of seeing them. There's no chance of taking a photograph. The conditions have to be just perfect, where the planet is off to the side and we can cover up the light from the star and therefore see the planet. But one of the coolest things that we have taken a photograph of is what you're looking at right now. 4 planets orbiting around their host star. This video, you can see, it took years and years to create, so it's a time lapse. Planets don't necessarily travel quite that fast. You can tell that the star itself is being covered. It has this black circle around it. Even still, some of the light is glaring off of the telescope. But there's 1, 2, 3, 4 exoplanets orbiting around this star that we've got images of. Maybe if we get bigger telescope, better camera, we'll be able to see these planets in a little bit of detail rather than just specks of light. If you want more information on these 4 planets, there you go. The second way that we find planets is what's known as gravitational microlensing. we're going to get to Einstein's theory of relativity later this year. We know that objects that have gravity bend space, and light wants to travel in a straight line. However, when space is bent, that light is going to travel through that bent space and appear to bend. If light is traveling out from a star, it's going to travel in a straight line until it passes by a massive planet, and that planet can actually cause the light to bend just a little bit. And when that light bends, it can overlap, and we get a light curve, which is just a plot of how bright we're seeing a star, that looks like this. And when we get this little spike here, that tells us that there is something around that star that bent extra light into our telescope. So let's take a look at this little video one last time. You can see light bending. Here's Earth. We're going to get more than one light beam focused on Earth. That's where we get that little peak. Because gravity is going to bend light, we can actually detect that here on Earth. So what are some pros of this? You can detect exoplanets, which is pretty cool. Sometimes free-floating planets that are not around a star. So a planet that was slingshotted out as its solar system was being formed. And they're just flying through interstellar space with no host star. Sometimes one of those will pass in between a star and us. All of a sudden you get one of those light curves, and we just found a planet traveling through space that we would never have known existed before. When I did this class last year, we had found 53 planets this way. Now we found over 100. So it actually doubled in the last year, the number of planets that we have found using gravity to bend light. Astrometry. This one is the weirdest word. It's part astronomy, part geometry. I don't want you to be scared though. It's not really have anything to do with math. It has to do with where these stars are up in space. In order for this to work, you have a very large planet. And when you have a large enough planet, not only does the planet orbit around the star also kind of wobbles in its orbit. The sun does wobble because of Jupiter. Jupiter is large enough that it causes the sun to wobble. Well, if the planet's even larger or the star is smaller, the wobble is going to be more pronounced. It's going to wobble more. And if the star is wobbling in space and we are angled directly above or below that star, we can actually detect that wobble by comparing it to distant stars that are not wobbling. And if we see a star that is wobbling, we can determine how fast it's wobbling, and that tells us how much mass that other object has, which is one of the ways that we find black holes. If it has a small mass, it's a planet. Big mass is going to be a black hole. But if it has a small mass, we can tell that there is a relatively large planet orbiting around that star, which then causes that star to wobble up in space. To date, we found a single planet this way. Just one. Not the most effective way, but we have found one planet. So what are the pros? Exoplanet. Not multiple, just one. It's very hard to do. It doesn't work well with Earth-based telescopes because our atmosphere is going to make that star appear to wobble more than the planet does. So you have to use a space telescope, and that means that it's very expensive. It's still very difficult to do. You have to be directly above or below the planet to even see that wobble. We've only found one of them this way. Of course, that planet has a name, and that planet's name is Dennis. Raise your hand if you expected that planet to be named Dennis. But yeah, Dennis is the only planet that we found using astrometry, at least so far. Before we can go on to the fourth way that we find exoplanets, and the last one that we're going to look at today, review on the Doppler effect.
Notice how the sound changes pitch? As the police car approaches you, the sound is at a higher pitch than normal. The sound waves are being compressed or squashed. Then, as it moves away from you, the sound waves are longer, so the pitch is lower. This is called the Doppler effect, named after the Austrian Christian Doppler, who pointed it out in 1842.
You guys all have experience with the Doppler effect. You know that when a car goes by really fast, it makes a increasing pitch as it's coming towards you and then a decreasing pitch as it's moving away. And the reason is that that object is giving off sound. And if it's giving off sound and moving towards you, it's going to smush those sound waves together. Higher frequency, smushed together sound waves is a higher pitch. As it's moving away, it's going to release those sound waves as it's going in the opposite direction, and those sound waves are going to seem to be farther apart, which make a lower pitch. That's the Doppler effect. It also works with light that we're going to talk about. And if you smush them together, it's a higher frequency. And what is the highest frequency of visible light that we can see? It's blue. So it's going to appear to move towards the blue end of the spectrum. And we call that being blue shifted. If that object is moving away from you, those light waves are going to seem to be spread out. It's going to be a lower frequency and therefore a longer wavelength. What color of light has the lowest wavelength? Well, that's red. So if an object is moving away from us and the light is being stretched or spread out, that's known as being redshifted. If the light coming off of an object is shifted towards the blue end of the visible spectrum, it's known as blue shifted. We know that object is coming towards us. If the light from that object is shifted towards the red end of the spectrum, then it's known as red shifted. We know that object is moving away from us. We're going to use that bit of knowledge for the rest of the year. When we start talking about objects out in space, are they coming towards us or away from us? We just look at the light. Are the light waves being smushed together? It's coming towards us. It's blue shifted. Are they spread apart? It's moving away from us. It's red shifted. With that in our brains, let's move on. The next one is known as the radial velocity technique, and it's related to the one that we just talked about. If a planet is big enough, it's going to cause that star to wobble. Similar to somebody out in track and field that's throwing the hammer. Because the hammer has a bunch of mass, the person twirling around with it is going to seem to wobble on their axis. Stars do the same thing. And instead of looking at it from above and seeing it wobble, instead, what we're going to do is look at it from the side. And if the star is now wobbling, it's going to wobble away from us, and the light will be red shifted. And then it will wobble towards us, and it will be blue shifted. And then it will wobble away from us, and it will be red shifted. And if the light from a star is red shifted, and then blue shifted, and then red shifted, and then blue shifted, and it does that repeatedly, we know that there's something causing that star to wobble in space. It's a planet. We can time how long it takes between red shift, and then back to blue shift, and then back to redshift. That would be one orbit of that planet. And if we know how long it takes for a planet to orbit, we know how far away that planet is. If we know how far away it is, we can determine if it's in the habitable zone. And then we can actually determine how bunched up it is and how spread out it is. So we can determine how much it is wobbling. If we know how far away the planet is and how much it's causing the star to wobble, we can actually determine how big that planet is. Depending on how big it is, we can determine what it's probably made out of. Is it a gas giant? Is it a rocky planet? So by looking at the light being smushed and spread out, we can find a planet, figure out how far away it is, figure out its orbital period, figure out what it's made out of, figure out if it's in the habitable zone where it could have liquid water. All of that information astronomers can get just by looking at the wobble of a star. This is what I want you guys to write down for this. If a star is moving towards us, the light will be blue shifted. If it's moving away from us, it will be red shifted. If it does that repeatedly, we know that there is a planet going around that star. The first ever planet that was ever found, 51 Pegasi b, was found using this method. This is actually the light curve from 51 Pegasi b, where the velocity is going away from us and then towards us and then away from us. And they were able to calculate, because it repeated, how long that took, how far away the planet was, how big the planet would probably be based on how much it was wobbling. So 51 Pegasi b, the planet that we just learned about, was found using the radial velocity technique. This is the second most successful way that we have to finding planets. The first planet we ever found was using this method, and we have found hundreds and hundreds of exoplanets using this. Last year when we did this, we had found almost 20% of all exoplanets using this method, over 660 of them. This year, however, That number went up a little bit. We went from 660 to 821. So in just 1 year, we found 160 new exoplanets using the radial velocity method. And now you guys get to practice it. This is on Canvas. It's due tomorrow night. Have fun. I mentioned the radial velocity method is the second most successful way of finding exoplanets. Tomorrow, we're going to go over the number one most successful way of finding exoplanets.